A company called Evergreen. Colonel Peoples can tell you all about them probably. They were going from Carswell Air Force Base, which happens to be where Matt and I are from, up to Tinker Air Force Base in Oklahoma. Their cargo is 5,000 rocket igniter fuses. So before anybody even goes near this investigation-wise, who do we have to go out and have deal with this? Well, actually we got a name for them in the military. DOD. Those guys are crazy, but thank God for them, because they're the guys who go out and fish all the stuff that'll blow me up out of the scene. They got to sterilize that place, make it safe to investigate before we go near it. These guys took off out of Carswell, and about 8 minutes after takeoff, radioed back that the cargo door, this is a freighter, cargo door opened up. On this DC-9, that cargo door is a side-loading door in about the middle of the front fuselage that's 20 feet long by about 8 feet high. What do you think that did to the airplane's ability to fly? Rolled them over, they go straight into the ground.
Why did it open?
Huh?
Why did it open?
Latch failed. They did find enough of the latches to indicate why. Now, this thing's buried into a vertical column 12 feet deep. What kind of expertise do I have to bring in to diagram this thing and preserve the evidence? Who goes out and very gently, layer by layer, archaeologists, exactly right. And there are folks out in the world who do forensic archaeology, who assist with this type of thing. Because that's the sort of expertise you might have to have with something like this. Because if I go digging it out of there, I may get it out of the hole, but I'm probably going to destroy the evidence. So I need somebody who's capable of preserving it. Okay. One of the other ways we have for sometimes figuring out what happened is called ballistic trajectory analysis. Now one, this was originally invented by NASA. If you have ever read any history about NASA, or watched The Right Stuff for that matter, great movie. In the early days of NASA, what did they have a lot of problem with? Rockets blowing up. And originally they developed this idea back before we had really sophisticated computers to figure out how the rockets came apart. Based on where the wreckage on the ground was, and what you literally did was you do a grid survey like we talked about, and then apply all of the forces that make things move, put it back in the air, so that we can understand the breakup sequence primarily. But we have to start with that grid map position. Then we've got to use radar information. We've got to use weather data, fall characteristics of debris. That's a subspecialty of physics. Ballistic aerodynamic characteristics. How does something like a sphere fall? Like this thing.
It drops.
It's going to follow pretty well a flight path. The trouble is it starts spinning in flight, which creates what? Creates lift, which means it's going to go downstream a lot further than I would expect it to. How's a wing going to come off? And what's it going to do? If it doesn't have a landing gear on one end, wing's going to flutter down like this, like a leaf. Which means if I've got winds blowing it sideways, where's it going to be? Downstream. If I have a weight on one end of the wing, like a landing gear, it's going to spiral down, which means it's going to be at a different place. Now what I have to do is understand all of that, and then theoretically I can put it back in flight. The two cases where we've used it pretty effectively, TW-800. Now most of you probably weren't old enough to remember 800, next slide please. TW-800 was a 747-100 flying from New York, JFK, to Paris. 230 people on the aircraft. 13 miles, or 8 miles rather, off of Long Island. As it's climbing through 13,700 feet, the aircraft exploded. What you're looking at here is the composite radar map of the debris. Every single one of these pieces is a piece of that airplane at this horizontal slice. of air. Now the advantage the investigators had with 800, there's a lot of eyes watching that airspace. You probably can't read all this stuff, but there's a lot of military radar involved in producing this composite, which also is how they know a little bit more about what happened to the Malaysian airliner, but I won't bring that up again. Anyway, every single one of those pieces is a separate piece of an airplane. What does that tell you about the breakup? Pretty catastrophic. It's going in this direction, and what ultimately the NTSB was able to develop and produce with a lot of help, next slide, is this. Long Island, airplane going this way. This white line is the flight path of the aircraft. It is level at 13,700 feet. First event happens here. This first debris field is about 3/4 of a mile by 3/4 of a mile on side. It's in 200 to 300 feet of water. So what's the first thing we got to do? We've got to bottom image everything before we've got to create that grid map on the bottom of the ocean. And then what I've got to do, or what we have to do, is pull that structure off the bottom, put it back to the surface of the water. Because when the airplane hits the surface, that doesn't mean everything's over. As everything settles down toward the bottom, what are the ocean currents and sea currents doing to it? And now I've got the field of hydrodynamics instead of aerodynamics. Because remember all those aerodynamic parts, and I told you a few of them, how they descend through the medium? They do the same thing in water, they just do it slower. And to find that debris field, I gotta map all that stuff out, apply the drift forces to it, put it back on the surface so I know approximately where those pieces entered the water. The yellow part is the front end of the fuselage. It says nose section, but in reality, that's everything forward of the wing box. How many of you have heard of TW-800? Other than the conspiracy theories, okay, a few of you have. I can tell you right now, this is not a bomb, it's not a missile. It's a fuel-air explosion in confined space. Now, one of the 3 sets of folks next week better remember that.
I will.
Fuel-air in a confined space, distinctive characteristics, bulging and rupturing. Gasoline has a tremendous amount of force if I contain it. I can make it explode. But the difference between a fuel-air explosion and one produced by a detonation is tremendous. Fuel-air explosion, I produce a blast wave, but the blast wave is associated with the rupture of the container, not from a chemical agent propagating a supersonic shock wave. Evidence very different. What we see with 800, that forward bulkhead on that center fuel tank, which is the wing box on the airplane, bulged out. And these guys have seen that airplane. And that's all characteristic. Did you see all this area in red? Everything that's found in there is from that center section of the airplane. The nose section, the big frame on the leading edge of the wing box, that whole frame starts unzipping the rivet line. And it unzips up to about 11 o'clock, 2 o'clock. What does the whole front of the airplane do?
Fall apart.
Comes off. No, it didn't explode.
No, fall. Like as
Falls off, yes,
yeah.
exactly right. And kind of spirals down like a bullet. Very small, very compact area. Mostly impacts the surface, does break up, but sinks rather quickly. Notice this little climb area here. That's what fueled a lot of the conspiracy theories, because the airframe actually climbed to 15.2 before aerodynamics took over. Why did it climb? No, not the hole, more basic. Less weight where? Denny, you taught them about center of gravity effects?
We just did.
Okay, there you go. Here's a good example. I pull the front end off the airplane, where's my center of gravity? Back in the tail. Pitch up. This is a 100 series 747. Those engines are still running. The people in the back of the airplane probably had an e-ticket ride because they survived most of the way down. But that third debris field